Hi, everyone. Welcome back this week. This week, we'll be finishing out our discussion of regression and correlation. And I know we learned a lot of materials last week. The notes are rather long. These notes are rather long too. And so I'll just say up front that, not everything in these notes this week and last week are going to be on the final. And I will be very clear with what is on the final. But basically, if it's on the homeworks, that's really most of the information you're going to need. So there's some stuff, for example, multiple regression that I just will tell you in the notes that's not on the exam. So I would say, unless I say it directly, look at what's in the homework. If it's in the homework, be prepared for it on the final exam. If it's not on there in the homework, you can ask me, but probably won't be. But conceptual things could be like, you need to know that simple linear regression assumes there's a numeric X and Y, which I guess the notes do say, but if there's any gray area, let me know. So last week we got introduced to simple linear regression and correlation, and we learned that they're both really, really similar. In fact, exactly equivalent procedures. And let's start with how they're similar. First, they're bivariate techniques. And in particular, bivariate means where they're suitable for comparing two different variables. But going further, the correlation and simple linear regression model, they're really suitable for comparing two numeric variables. And so, we learned the chi-square test, which is suitable for comparing two categorical variables. We learned t-test, which is comparable for comparing one numeric variable to one binary categorical variable. And so this week and last week, we're starting to learn methods for two numeric variables. And, if you continue studying statistics, we're going to very quickly, like you would spend the first week or two studying simple linear regression, which is what we're ending this course with. And you would start talking about multiple regression for the rest of the semester. And multiple regression is similar to simple linear regression, except it's multivariate, not bivariate, but multivariate. And that means there's many X's and one Y. There's a type of regression where you can have multiple Y's, but you won't learn that for a really long time, called multivariate regression. Sorry, multivariate's used in a different couple of ways. What I said was kind of confusing, but just you can have multiple outcomes, but that's you'll learn that in the future. So I like to think of multivariate just meaning you're using multiple X's or Y's. And so in particular, multiple regression means many X's and one Y. So this material is going to be optional, but the reason why I think it's important for me to say a little comment on it is because this will tie all the material you've learned in this course to what you'll be studying in the future. So to really make that a very direct, tying together of what I hope you'll study in the future as you continue studying statistics and what we've learned in the class, just making sure that those two things are tied together for you. So let's get started then with the correlation and linear regression. In particular, what we're going to be talking about is how we can make inferences. So when we talk about statistical inference, there's a few different ways we've thought about inference this semester. First, we've thought about estimation. You could be just trying to estimate a parameter like mu or beta 0 or beta 1. These population parameters we write in Greek. They're the unknowable things that researchers want to know about. They're the unknowable things that we want to make claims and inferences about. We can also do interval estimation with confidence intervals. That's all still possible here. There's a little note in confidence intervals in these lecture notes, but I'm not going to cover too much about confidence intervals in a regression context or correlation context, but it is possible to get those confidence intervals for these types of statistics. And then we've also learned hypothesis testing. That also falls under this broad category of inference. And so we'll learn about how to actually conduct some hypotheses tests. And remember, we're assuming we have two numeric variables, X and Y, and the hypothesis we really want to evaluate is, are they linearly associated or correlated? And so, as usual, when we start talking about hypothesis testing, we need to start talking about the error, and in particular, the standard error. If you remember the t statistic for the t-test, so the independent samples t-test, it's the statistic of interest, which is the difference in the two groups. And then in the bottom, we put the standard error of the standard error of the difference statistic. So here you can, again, you can see the difference statistic in the numerator over the standard error of D bar down here. And also when we did the mean, when we talked about the mean, we talked about making inferences about the one sample. We did the statistic look like this: X bar minus mu over the standard error of X bar. Now remember, minus mu, that depends on the, sorry, I put a bar above it. I don't need a bar above mu there. That will usually be given in the problem. And it's possible too that you might be testing like, is the mean 0 or something. So sometimes that will fall out if you're doing like a one sample t-test, but often like you'll be testing is, does the mean level of production say 10 items per hour or something like that. But anyways, what I want to emphasize is that you have something in the numerator, this usually with the statistic of interest like X bar, the difference of X bars, and then always the standard error in the bottom. And so this is why we're studying standard errors here, and we've talked about them every week. We will often introduce a statistic, and then shortly thereafter we introduce the standard error. Now remember, in one word, the standard errors really means the accuracy or precision of your estimate. And there's many things that affect the standard error, and what we're going to talk about next is the standard error and a few things that affect the standard error of the regression slope. So again, these things have distributions. That's why they have error. So let me clear all these drawings. So the two statistics this week, if you have a regression line, right, remember that we can write the regression line like this. Y hat means my predicted value of y equals, we've been writing little a plus little b times x. So these are my estimates. So little a is my estimate of the alpha parameter, and little b is my estimate of the beta parameter. So again, statistics, while these on the right side are our population parameters, and the definition of a statistic, as it has always been, is you take a random sample, and then based on your estimator or formula for alpha and beta, you estimate these things based on that. And last weekend, we talked a lot about how do you, what is that formula for alpha and beta, right? So the homework last week, for example, had you find a line of best fit and interpret alpha and beta. And so again, these are parameters. We gather statistics to estimate them. And so what this means is all the parameter is not a random variable, although the parameter is fixed. If we look at the beta parameter, if we take estimates of our b, the b is going to have a sampling distribution that is a normal distribution. And that's because, again, you have a random sample, so you're going to get a b estimate there, someone else can get a b estimate there, someone else can get a b estimate there. But on average, the little b's in that distribution, the sampling distribution of little b, will actually be the true population parameter beta. And so again, that's what a sampling distribution is. And you can see here, we've given you the sampling distribution for both the slope statistic and the intercept statistic. Now, we need the standard errors to do hypothesis testing, but there are a couple of things that the standard error formulas will tell us. First of all, if the residuals or errors in our data are normally distributed, then the distributions of A and B up here are also normally distributed. Notice how they have little n's there. Remember, that means the squiggly n, that means distributed as a normally distributed variable. Then they have the mean of the distribution is the relevant parameter you're estimating. And then there's variance. And remember, the standard deviation, that's what the standard error is. The standard deviation in this distribution is actually the standard error of the sampling distribution. So the first thing we'll note is that the distributions are normal if the errors are normally distributed. Normal distributions make our life a lot easier for reasons I'm not going to go into in these notes, but we'll just say that when these A and B have a normal distribution, we can create confidence intervals, we can interpret p-values and all of that. I'll talk about assumptions briefly at the end of these lecture notes. Furthermore, both A and B are unbiased. We know that because at the center of this little a is the alpha parameter, at the center of this little v is the beta parameter. We typically want unbiased estimators, which means these are two estimators we want to use for A and B because they're unbiased. And then the sampling variance for both A and B is a function of three things. The first is the regression variance. So I talked a little bit about this last week. As R squared goes up to 1, the regression variance goes to 0. So if you can think of R squared as a measure of model fit, the regression error variance, it's actually the degree of misfit. As it gets bigger, you have more error in the model. So this is something that's really important in future statistics. So I want you to be kind of familiar with it now, but we're going to reference it and talk about it today, but it's nothing that I expect you to have a huge comfort with understanding and interpreting at this point. There's also in these formulas, the sampling variance for A and B, they depend on the variance of X. That is, the more variance in X you have, the more precision or less error you're going to have in the B and A distribution. And that should make sense. Say you want to estimate how age relates to income. If everyone in your sample is 30 years old, that is, your X has no variation, I'm not going to be able to really get very good reliability in my estimate for how does income change as age changes, right? Because there's no variance in X. X is just basically always 30. So we're asking too much of the model. And so you'll notice that if there's a lot of variance in the IV or X, that is SX squared. So the denominator here of both the standard errors. So more variance in X means less error variance in B and A, less sampling error. And also the sample size, that's also the denominator. So as your sample size gets larger and larger, you get better estimates of A and B. The error gets smaller and smaller. So, we've looked at really briefly, not into a lot of detail, but I was just talking about the sampling distribution of A and B, the intercept and slope parameters, but really what we care about is B, because the intercept is often not going to be of a lot of interest in the regression context. So really what we want to do is we want to talk about how we make inferences with the slope. And the reason we'll do this, imagine I have a null hypothesis, like where I set it up like this. The null hypothesis is that beta equals 0. Remember, in a linear regression line of best fit, beta is the slope. What does a slope of 0 actually mean? Well, in a linear case, when we're talking about the slope, it means that it's a perfectly flat line. And if you really think about it, that's the definition of no relationship between X and Y, right? As X goes up and up and up and up and up, Y is just not changing. It's just hovering at the same level, right? So if there's a 0 slope, that means there's no linear relationship. So really what we're interested in testing is this null hypothesis versus this alternative where beta is not 0. Because if beta is not 0, well, that means there's a slope or an association between X and Y. So this is why we're interested in particular at looking at the standard error of the slope. And so you don't need to focus too much on the details of the standard of the slope. I would read these notes once over, go very slow, absorb the information. But the reason why we are talking about the standard error of the slope is because it's needed to make an inference about whether the slope estimate for B is statistically significant or statistically different than 0. And so it turns out that we can if we want to create the null alternative, which I just had on the screen, that is the null of beta equals 0. I want to compare that. Sorry, that should be O against the alternative. Beta is not 0. Well, I have this test statistic here. It turns out that if I do the estimate of B minus my null hypothesis value for beta, and I divide it by the standard error of beta, sorry, of little b, turns out that this has a t distribution. Remember, if we know the test statistic distribution, we can now start making inferences about and conducting hypotheses tests. As long as the assumptions of these tests are satisfied, we can be safe in doing this. Now, the cool thing is, this will often reduce because what is beta 0? That is the null hypothesis value that we usually test. Well, we test it being 0. So really that zeroes out. So what that leaves you with then, you get your observed t statistic. It's the estimate for B over the standard error of B. And you will always use SPSS to get these answers in real life. So I haven't, in this case, I'm not expecting you to really, I'm expecting you to be familiar with the logic of how you conduct test of linear association with the slope. But what I really want you to use in this class is correlation test. You should use the correlation test of linear association, which we're going to go over next. So this gives us a t statistic, and you can also see the degrees of freedom. Remember the t statistic, it's a distribution. The t distribution looks like this. It's always centered over 0. And depending on its df, that's all you need to know about the t distribution. So we're going to be using our t table again, always remembering that there are n minus 2 degrees of freedom. Okay. So there's a little call out box here if you want to read about why we use n minus 2 rather than n minus 1 degrees of freedom. You'll notice that like when we did the variance and standard deviation statistics, you'll notice they have an n minus 1 in the denominator. You'll notice in the covariance formula we looked at last week, there's an n minus 1 in the denominator. So n minus 1 is a lot, maybe perhaps more common. You'll see that more commonly, but degrees of freedom come out with the number of unique pieces of information in the data. And so we're basically estimating two things, the slope and intercept parameters. So we actually lose 2 degrees of freedom, but ask me if you want to go into more details, but I'll say worrying about DF, you need to know how to calculate it, where it comes from, but it's never really a super important thing to worry as a student about too much. And so with that, that's basically a wrap on how we do the hypothesis test for a simple linear regression slope, the beta parameter. And I'm going to come back and actually show you how to do this in SPSS shortly. So you can see a live example. Lastly, we can construct confidence intervals. You can B is a statistic with a sampling distribution. You can conduct a confidence interval of any statistic. So you'll always be learning about confidence interval and hypothesis testing as you get introduced into new types of statistics in the future. They always come hand in hand. So I will not be emphasizing the confidence interval approach for the slope parameter in the 2 weeks that we're studying regression in this course. Okay. So we talked about at a high level how you make what you conduct and how you set up a null and alternative test when you're testing the slope parameter. But the one that we're really going to test and the one I'm going to test you on in your homeworks and your midterm is conducting a correlation test. It gives you the same exact answer, but I view this class as like an intro to the more advanced modeling course, regression-based modeling. So in this course, I've really remained focused on bivariate and univariate statistics. That's the foundation you need to go on to multivariate type statistical problems. So for now, I'm not expecting you to know, other than just at a high level, testing the slope being 0, why 0 is a good test of meaning no relationship versus a slope meaning there is a relationship. Just understanding that logic and theory is all I'm expecting you to do now. When it comes to testing linear association between X and Y, go to the correlation test. So just as we've been talking about, the correlation is a statistic. By definition, statistics means you've gotten a random sample and you've calculated some number. Little r is an estimate of the parameter rho, which looks like a little p. And so we want to make inferences in the case of the correlation statistic about this parameter p. So if that's what we want to make inferences, how do we do that? Well, we'll first say that there's a few different types of inferences you might be interested in making. First, you might want to know, is there just a linear association between X and Y? In that case, could rho be 0? Or is it some non-zero value indicating there would be a relationship or slope between X and Y? But we could also test whether the correlation is positive or the correlation is negative. And you'll notice that the alternatives, they have the directionality. Just like before, the null is always the parameter equals 0. The alternative can be not equals to 0 or be directional like this. So if we're going to be conducting a hypothesis test of the correlation statistic, we're going to go through the same 4 steps that we have been going through the last several weeks. So that means the first thing we do is we'll set up our null and alternative test, and we're going to see examples of how to do that in a second on an applied example. But you can see there's really 3 options you have depending on the research question, right? Step 2 is you decide on your alpha level. If it's not stated, you use 0.05. You can't have a 1 or 2-tailed test here, so you need to keep that in mind. Then, as usual, step 3 is compute the test statistic. The observed test statistic equals the correlation divided by the square root of 1 minus r squared, that is the correlation, over n minus 2. So that's what we do in the step 3 to get our observed test statistic. And then finally, step 4 is you make a decision, is it significant or not? And you can do this one of 2 ways. You can use the p-value approach. So you see, I took this image from the book. They describe the p-value approach. Definitely come talk to me if you're not familiar with that, but we've talked about the p-value approach before. You can also do the rejection region approach. So that's the critical value approach on the left side here. That's how I've done most of the significance tests with you this semester. But once you leave this class, you will almost only use the p-value approach. So I will cover both in an example problem next. So let's say you have 10 individuals and you've reported the depression and anxiety, and this is the data. And you want to know whether anxiety and depression are positively correlated. Let's test this hypothesis at the 0.05 level of significance. Okay, so let's look at the first solution we have here, which is conduct a correlation test. So step 1, what are the null and alternatives? The null will always be the correlation parameter rho is 0. In this case, it's a directional one-sided hypothesis because I said the research question here, we're looking for are they positively correlated? That means we can put all the alpha on one side in the positive direction. So I'm looking for an alpha with 5% area on the right tail in a t-table with a df of 8. So I'm going to go to my t-table and look up the df of 8. I'll find 1.6 is the cut value that leaves 5% area in the right tail. So I've made my rejection region, and 1.86 represents my critical statistic, right? Now, step 3, I need to calculate the test statistic. There's 2 steps here. First, I need to calculate the correlation R. Then I need to use that to calculate the observed test statistic. So in looking at the correlation formula for from that we learned last week, it's the sum of the products of the deviations divided by the square root of the sum of the x squared x deviations times the square root of the summed of the sum of squares of the y's. So here we have x minus x bar, again, 19 minus 10.5, 8.5. 4 minus 10.5 is negative 6.5. So forward. So you should be able to make those 2 columns. This is the product, 8.5 times 4.9, etc. You square them, right? And so you're basically, you have the formula, you're matching this. So this is the sum of the product of the deviations. So this is the product of the deviations, deviation 1, deviation 2. This is the sum. So that 219 comes up there. The sum of the squared deviations of x, 250.5. The sum of the squared deviations of y, 214.9. So you're plugging that in, you get a 0.95 correlation. That's a very large and positive correlation. It's probably going to be statistically significant, right? It's really close to 1, very strong. Let's go do a test here. So the observed statistic, now that I have R, I just plug in R to the formula. I get 8.6 as my observed test statistic. This is way bigger than the 1.86. Therefore, I conclude that anxiety and depression are linearly related. And I also conclude the correlation is large in magnitude. Now, we can do this in a regression framework also. So I have a second way of doing this, and step 1 and step 2 are the same as before. But now my observed statistic is going to come from the observed t statistic. It comes from comparing a different hypothesis. Sorry, I said the hypotheses were the same as before. They're not quite the same. I'm testing here whether beta, the slope parameter, is 0 versus not. It actually means the same thing. You get the same p-value, but it does mean we have a different test statistic. And so here it's going to be little b over the standard error of b. The standard error of b depends on a few things, and you're not going to have to compute the standard error of b in this course. So I wouldn't worry about it too much, but I put the math here and, but you can see I'm making my estimate of b is 0.087. I got that from applying that formula. So anyways, I get a b here of 0.87, a standard error of b of 0.098. I put that together, get 8.87. So notice that this observed t statistic, it is a little different than the 8.6 I got up here, right? And there's just rounding error because like how many decimals do I put here? And then I'm square rooting it, and the decimals matter a lot in square rooting. So you're going to get some variability, and I'm going to be very generous with not counting you off for rounding issues. So just work with me here, and I will work with you as well. In practice, you don't have to worry about this because you're going to use software, and software makes good default decisions about rounding usually. So here the observed statistic is bigger, the 8.87. So we're going to reject the null and conclude there's a linear relationship there. Okay, so that's that. Now, I also wanted to show you an example of how to do this in SPSS. So I'm going to switch gears and show you how to do this in SPSS, but you can see the output. Let's look at the output before I show you how to do this in SPSS. Again, this is optional, the SPSS content, but it can check and give you these answers, right? If you can use SPSS in these small limited ways we're learning. So you can see here, I get the 0.95 estimate. It's the same. You can also see I get a p-value, and you can tell it's telling me the two-tailed p. So I get the same correlation, 0.95, computed up here. Also, my p-value less than 0.001. That's APA format, and so you'll just see that's how they're putting it in SPSS. And then if you ask for a linear regression, you're going to get the regression slope 0.872 and the standard error 0.098. And you'll actually see I got those same things, 0.87, 0.098. And then my t statistic, I got 8.87. They get 8.88. So again, some rounding error, but they're getting similar t statistics. But look, our p-values are all basically the same. So like the 10th decimal are the same. So, we're going to report the same p-value as less than 0.001 here. So how do I actually do that? Well, if you've got SPSS open, which takes a while, you can just input the data here, and you can copy and paste the data in fact, and then I came here and changed depression and anxiety there. And then, I usually like to come in scale, make it a little safer running these procedures, since sometimes some procedures will ask for that. And you're going to go to analyze. The first thing I'll do is go to correlation. So I'm going to go to correlate by variate. And you need to just arrow them both over. And look, if you go to options, you can ask for means and standard deviations if you want. You can also ask for the confidence interval there. As you can see, I don't think we need to do that. You can ask for if you want a 1 or 2 tail test. So if I hit OK, I get that little correlation table, right? Shows depression's correlation with anxiety and anxiety's correlation with depression, which of course are the same thing. So correlation matrices have a property of symmetry. So you only have to look in the upper or lower part of them. Now I can also do a linear regression. My DV here, I'm going to make it depression. That's the Y. The X, I'm going to make anxiety. And I did that because that's actually specified in the problem. Just show you. Actually, I guess it's not. I just specified that myself. So in simple linear regression, it doesn't matter what you make X and Y. You're going to get the same p-value, but the regression slope can be a little bit different. So I will warn you on that. But in theory, you're assuming one is Y. That is, one X is driving the Y. That's an assumption you're making. In any case, you can see you get the same correlation. You get R squared here. That is, anxiety explains 90.8% of the variation in depression. You get the correlation, and you get your regression line. Okay. So that's how we can do correlation test or a inference about the slope parameter in SPSS. Very useful, but not required to know for this course. Okay, and now I want to spend a couple minutes talking about the phi correlation. So it turns out that we have been talking about an assumption for X and Y that they're both numeric. But there's actually a really cool, we're going to learn two hacks next. First of all, it turns out that if X and Y are dichotomous means it's binary. There's a dichotomy, there's two values. It's a 1 or 0 variable. So what that means is that once it's 1 or 0, then there's actually this exception to the rule about the levels of measurement, where if it has only two values, then we actually cannot determine its level of measurement. That means it could be nominal, ordinal, interval, or ratio. And the cool thing about that is it means you can actually take a 0 or 1 variable and you can treat it as numeric. That means if you take two variables that are 0 or 1 and you ask a program for the correlation, it's actually applying the same correlation formula that we just have been using, even though both X and Y are not numeric. Even though they're both binary and categorical, you can compute a correlation. You can take the mean of the variables, you can take the standard deviation of the variables, etc. So that's a very useful technique. And it has a very famous name when you take two binary variables and run the correlation called the phi correlation. So the phi correlation is the same correlation we've been learning, that is Pearson's product moment correlation. But it's got a special little phi, Greek phi to denote it. We call it the phi coefficient. And it's a very special type of correlation because it's a correlation between two binary categorical variables. So if you have two binary variables like smoking, yes or no, gender, male or female, because they're both binary, you can run a correlation there. And you might be saying, this looks a lot like the chi-square test. And that's right, it is. You should get pretty much the same exact answer. I don't think you'll get the same exact p-value, but you should get really close. You could run this as a chi-square test because they're both categorical, or you could run it as a correlation test because they're both binary. Okay, and so the phi correlation turns out to have this little formula. If you have a 2x2 cells and you label them as A, B, C, D, the phi coefficient has this little shorthand formula, A times D, so you can see that's 23 times 26 minus B times C, 20 minus 14. And if you go in and you keep plugging in stuff, you can use that shorthand formula to get out your correlation. So that 0.19, you would get the same 0.19 within rounding error as if you use this formula. It's just with the phi, instead of going through all this, you can just use the A, B, C, and D little shortcut hacks. And your correlation is going to be interpreted just like R. So that's hack number 1, called the phi correlation for two categorical binary variables. Now, what if you have one numeric variable and you have one categorical variable that's one is binary. So it turns out that if you have one dichotomous variable and one numeric variable, you can still use this correlation statistic to get that bivariate association. So remember, if it's a binary and a numeric variable, you can use the t-test, the independent samples t-test, as long as you satisfy those assumptions. But an alternative is to actually conduct a correlation test. So again, these two hacks come from the fact that once a variable is 0 or 1, you actually can't tell whether it's what its exact scale of measurement is, as whether it's nominal, ordinal, interval, or ratio. And now last but not least, we have the coefficient of determination. So this was already covered last week. So this is just putting here kind of as a reminder, but it's extremely important. You're going to be reading a lot about R squared if you continue studying statistics in the future. But if you have a correlation of say 0.81, then if you square it, so you can see here we square it to get 0.656, that gives you the proportion of variance in Y that can be attributed to X. So 65.6% of the variation in Y can be attributed to X. So that's an important thing around interpretation. You're going to see psychologists and education specialists a lot. They do report these coefficient determinations. It's important to recognize that's just a squared correlation coefficient. And now we're going to come to the last regression topic that we'll cover this week, and that's multiple regression. So far, everything we've talked about in regression has been under a type of regression called simple linear regression. By definition, simple linear regression requires one X and one Y. But it turns out that you can make regression methods work for having a lot of X's or a lot of Y's even. And so the very next thing you would learn in your statistics education is exactly this multiple regression, where there's many X's but only one Y. And the reason this is important, because let's say you have X and Y and you plot this data. So I'm only looking at it in a bivariate lens. If I fit a regression line through that, you can see that the line of best fit is going to have a negative slope. That means it's telling me that as X goes up, Y goes down. But it turns out that in this data, there's actually an important grouping variable. And once you account for that variable, the slope within the groups is positive and linear, so not negative. And so this is why you want to be able to account for other third variables. We call them lurking variables or nuisance variables or confounders. They have a lot of names. That's why we want to be able to account for third variables. And so this particular issue, which I just presented, is called Simpson's paradox, where the regression slope literally reverses because you've incorrectly omitted in the simple linear regression estimate over here, you've omitted an important factor that cannot be ignored. So you'll read about Simpson's paradox, but the main reason it exists is because when you have a third variable that matters, as in this example, the estimate of X, the regression slope, we call it a partial regression slope because you've partialed out or controlled out or canceled out the influence of a third variable, which we can call Z, or whatever we want really, as you estimated the linear impact of X on Y. So again, the difference between a partial coefficient or partial relationship and one that is not partial. So this also extends to correlations. You can have a partial correlation. So to extend this in a regression model, all we have to do is just, before we had alpha, beta 1, x1, and then we had the error. When we wrote the full population regression model, remember we had that error in there. In multiple regression, you just add in an extra slope parameter for x2, an extra one for each x, and you can have as many x's as you want. There are limitations here based on sample sizes and whatnot, but in theory, you can go as big as you want. And so now what you've done is when you've added x2, x3, x4, this beta 1 is the impact of x1 on y controlling for x2, x3, x4. So B1 becomes a partial regression slope. And you can see here, It's the relationship between x and y holding constant all the x's. And so that's really the main thing I want to say about multiple regression. And you can see where it's headed. You've got population parameters, beta 1, beta 2, beta 3. And I want to know whether, this x2, is it linearly related to y or not? Is x4 related to y or not? And so that's where you would quickly go in a multiple regression lesson next, is you would start learning hypothesis testing for each of the betas. But we're not going to go that far. We're going to talk about the assumptions of regression. And I'll note that these are the assumptions of a multiple regression model. And some of these are not necessarily suited for simple linear regression. So this material on assumptions is additional material as well, will not be covered on homeworks or the final exam. So let's review a little bit. So there's 4 groups of assumptions. You'll see the assumptions grouped into all different kinds of ways and things. And so here, let's look at the first assumption. We've said it's an assumption about the model. So that is, there's linearity in the regression parameters. Sorry, this actually, I don't need this. And so what that means is that, like the beta and x, that's basically like a slope parameter. And even if I add in an extra one, beta 2, x2, it's still a slope parameter. What happens is you leave 2-dimensional space, you go into what's called multi or n-dimensional space. But these are still inherently slope parameters, and you interpret them the same way. This right here, you can see it has the x as like an exponent. That's not a linear model. So that's the first assumption, is that we're going to parameterize the model with linear coefficients. Secondly, the errors must be normally distributed. So the error distribution must be normal. So the error should be normally distributed. And the mean of them should be 0. The expected value should be 0. So if your regression line looks like this, the data is here, all of your errors are going to be positive, right? You can see here that y, the predicted value of y, is just above all the actual value. That will never be what your regression line looks like. So it turns out that a consequence, you don't really have to check this assumption because it's always true. The expected value of your residual is 0. You do need constant variance or heteroscedasticity. Sorry, homoscedasticity is what you want. I'm not going to go into that too much. That's really requires a full lesson on all these assumptions to get into checking it and looking for it. But want to make you aware that there is something called the homoscedasticity assumption, which is it's a number 4 here. This has been an assumption in many tests we've looked at this semester. So the observations are independent. That means the scores from one person or one, if you're studying schools, they don't influence the scores of the next school or person, right? So independence has been an assumption all semester. There are some assumptions about x's. These assumptions are really mostly that, you don't have measurement error, and there's stuff about the independence and the error terms. Again, that's really like a higher level stat course. So I wouldn't worry about the assumptions around the x's too much. And then number 9, you don't have to worry about too much, but all observations are equally reliable. So look, I'm giving you this so that when you study regression in the future, pull this up, read through these. And there's also a couple of more notes on the next page. That a lot of books will say that there are assumptions about the x or the y's, that is the dv's or iv's. Now, this is incorrect. There are none. There are no assumptions about x's and y's. And I've seen textbooks and professors say this. It's not true. The x's and y's can have any distribution, really. They can even be categorical variables. You'll learn about regression and categorical variables later. But one caveat here is that the regression assumptions, they really focus on the shape of the error distribution. So these group of assumptions are the main ones you're going to check, the residual assumptions. And so it is true that the error distribution has to be normal. And it is also true that usually when your DV is normally distributed, your errors are normally distributed too. So that's why some books will talk about the distribution of Y, but really it's the distribution of errors that matter. Okay, so that's all for this week. I will be posting a homework, and please remember that anything that you don't see tested on the homework assignments or anything that's not told to you explicitly via a Canvas announcement or document will not be on the final. So I will be updating mid-final expectations and material on it in the next week or two. So please be patient with me as I prepare for that. Thank you all. Hope you enjoyed the lesson today.